So the reflection is we want to make sure you do this reflection on your own, and then you can kind of look at what my reflections might be. These are, again, should be more personal than anything, but I'll give you what my explanations for these would be. So the area under the curve can represent displacement traveled, because one of the reasons we can look at is very clearly that if we take a look at the area under the curve, we calculate it using the height, v of t, times the width, delta x, okay? And that's going to be, or delta, we're going to call delta t, delta t, and that is going to clearly give us displacement. Velocity times time equals displacement. Okay, and we know that this area here is equal to, that is equal to velocity times time. Okay, so that area must then represent displacement. So how can we convert the dy by dx units back into y units? Well, if we take a look at dy over dx, if I multiply this by some dx, what I'm going to get is, what I will end up getting is dy. So we can multiply the derivative, okay, so f prime, that's why we talked about f prime as the height of the function, and we can multiply that by dx. And again, that area must represent some change in the original y function. Okay, so this is my dy by dx, right? That represented by the height of the function. The width of the function is our dx. Okay, the width of the rectangles is dx. And that area is equivalent to a change in y. And we can change that dy, the derivative, back into y units by multiplying by the change in x. So in the velocity examples, why are the rectangles only estimates of the displacement? They're only estimates because if we look at most of those examples were represented by curves. And when we took a look at those area underneath those curves, those areas using rectangles, there was this bit here, these bits that didn't quite match, right? Sometimes they're overestimates, sometimes they're underestimates. So they're only estimates because the rectangle shapes don't actually fit the curve. But what would make this more accurate calculations? Okay, that would be smaller rectangles. That's a big idea. Okay, if I make these rectangles smaller, okay, so if I make these rectangles, let's make them black. If I make these rectangles smaller, that area difference now changes. Right? The parts that don't match are less. So we have a much more exact way of doing it. Is there a way we can make it more? Is there a way we can make this exact? Well, we could make it more exact by making it narrow, right? By using narrower rectangles. What's the limit that we can go to then? How narrow can we go? Well, we want the width to essentially go to 0. But there's a problem. Once we have 0 width, we have no area. Okay, so well, this is a bit of a problem. But we did use a limit when we ran into the same problem with derivatives. Because if you recall, the derivative was when we let the change in y over the change in x, and we used a limit as delta x went to 0. Okay, so this is something that we saw before. So does it relate to differentiation? Yeah, that relates to differentiation through this. We use this delta x go to 0. Now, this is in derivatives. This is derivatives. Now, we're going to do something slightly different. We're going to say that sum of our dy by dx, or we're going to say f prime times delta x, right? And we're going to let that sum, and we're going to say from a to b, from x equals a to x equals b. And we're just going to say, yeah, let's just make these rectangles go to 0. So we're going to do the same thing. We're going to let delta x go to 0. And if we could do that, we will get exact values because we're going to make it narrower and narrow. And this is our area calculus, or which is called integral calculus. And this is what we're going to start looking at. We're going to start looking at these areas, and we're going to start summing up these areas in a more concise way. And we're going to use a limit and say that if we use a limit to do this, now we're talking about exact areas. And we're going to relate these exact areas to something called an antiderivative, but this is later on.